All right, so if I remember, this thing not showing is properly. Okay, so last time, as I recall, I think we did this example. I think this was the very last thing we did. Correct me if I'm wrong. Okay, good. So that problem had to do with heat capacity, and we're going to talk about specific heat. Get this thing out of the way. And when it comes to specific heat, this is the equation that we're going to use. Q, which is the amount of heat change for a substance, is equal to mass times the specific heat times the change in temperature. All right? Now remember, change of anything is always the final value minus the initial value. And that is no less true for temperature, right? So the change in temperature is the final temperature minus the initial temperature. And therefore, if the final temperature minus the initial temperature is positive, which means that the final temperature is greater than the initial temperature, that means that Q is positive as well. And the way we interpret that is that heat is being absorbed by the system. Then the opposite is true, of course. If delta T is negative, which means that the final temperature is less than the initial temperature, then Q is negative, which means that the system is losing heat, all right? So that's basically how we interpret the signs associated with the heat change of a system as it relates to the change in temperature. Now, we talked about the joule unit earlier, but there's another energy unit, which is called the calorie unit, which is still used to some extent, especially in fields like engineering. But it's not a metric unit, but there's a relationship between the calorie unit and the joule unit. According to the definition of a calorie, the water has a specific heat of 1 calorie per gram per degree Celsius. So this is the relationship between the joule unit and the calorie unit. 1 calorie is equal to 4.184 joules, all right? So you might get some problems. In fact, you have some problems already in the assignment number 7. No, number 6, I'm sorry. Which involves at least one problem where there is a question where you're given a certain value of energy in calories. And there's also another calorie unit. It's called the nutritional calorie or the food calorie. And the distinction that is made in terms of the unit is that we use uppercase CAL, well, uppercase C and then lowercase AL, as the unit to express the calorie unit, the food calorie unit. And the relationship between that unit and the calorie unit is 1,000 calories is equal to 1 nutritional calorie. And as suggested in the name of that unit, this is a unit that is used more often by people practicing nutrition. What else? Well, nutrition, let's leave it at that, all right? People in the nutrition field, they tend to use a food calorie unit. Okay, so this is just a list of different substances. And as you can see, they have different values of their specific heats. And one thing that will jump out at you when you look at these numbers is that water has a very high specific heat compared to the others, all right? And the main reason for that is because of a phenomenon known as hydrogen bonding, which we're going to meet later on in this course. What you'll find also is that metals tend to have relatively low specific heats. If you look at all the metals, silver, mercury, lead, iron, you'll notice that the one with the highest value is actually iron, and that value is 0.449. When you compare that to water, you can see it's very low, and all the others have low values. Aluminum is actually relatively high, higher than iron, 0.902. So that's the highest among metals, at least the metals that are listed here. Okay, so that's a point I just made. Many metals have low specific heat, and water has a higher specific heat than almost any other substance, again, due to the phenomenon of hydrogen bonding. Okay, so now we're going to look at some examples right here. It says how much heat in joules and in kilojoules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100 degrees Celsius. So the equation I mentioned before, I'm just going to write it up here. It's Q is equal to M, the mass, times the specific heat, which is represented by C, times delta T, right? So the question is asking for Q in this case. It gives you the mass. It gives you, well, it doesn't give you the specific heat, but you'd have to, that would have to be provided, which we indicated earlier, and the temperature change. Well, they didn't give us the temperature change, but they gave us the final and initial temperature. So basically, we're just going to put the numbers in. 225 grams times the specific heat of water, which is 4.18 joules per gram degree Celsius, multiplied by delta T. So delta T is the final temperature, which is 100.0 degrees Celsius, minus the initial temperature, which is 25.0 degrees Celsius. And we do the number crunching. This part here will work out to 75.0 degrees Celsius within the parentheses. And then for the rest of the calculation, we will take the 225 multiplied by 4.18 multiplied by 75. And this would have to be rounded off to how many sig figs? 3 sig figs. So according to my calculation, this works out to be equal to 7.05 times 10 to the 4 joules. And the question is asking for you to calculate the equivalent value in kilojoules, which I'm going to do down here. 7.05 times 10 to the 4 joules. We multiply that by the conversion factor where we have 1 kilojoule above and 1,000 joules below. So basically dividing the value that we got initially by 1,000. And the answer I got is 70.5 kilojoules. And that's basically how that is done. All right. Any questions about this? Okay, so the next example, it says what would be the final temperature if a 5.00 gram silver ring at 37 degrees Celsius gives off 25.0 joules of heat to its surroundings. And it says use the specific heat of silver listed in the table that we saw earlier. So the table gives you that the specific heat of silver is 0.235. I'm just going to write this down here. C is equal to 0.235 joules per gram degree Celsius. All right. So again, we'll be using the same equation that we used earlier, but this time what I'm going to do is I'm going to rearrange this equation up top here to solve. Okay, why is this not working? I'm going to use this equation here to solve for delta T. So when we do that, you're going to get delta T is equal to Q divided by M times C. Now, Q is 25.0 joules, but please note how the question is worded. It says it gives off 25.0. So that means that the sign for Q would be negative. So we're going to put minus 25.0 joules. And then we're going to divide by the mass, which is 5.00 grams. And then I'm going to multiply by the C for silver, which is 0.235 joules per gram degree Celsius. And let's see what that gives. 25 divided by 5 divided by 0.235. Okay, so according to my calculations, this works out to be equal to 21.2. So that would be the change in temperature. Now, that value would be equal to the final temperature, T2, minus the initial temperature, T1. What the question is asking for is the final temperature. So what I'm going to do is rearrange this to get T2 is equal to delta T plus T1, right? Now, delta T is equal to 21.2. 2 degrees Celsius. This is T1 here. And then I'll add T1, which is the initial temperature, which is, oh, shoot, I forgot. Very important. I knew I was missing something. There should be a negative sign here, right? So basically, I need to make a change here. I need to make a change here. Okay. So basically, it's going to be delta T, which is the minus 21.2. So minus 21.2, to which I'm going to add 21, I'm sorry, not 21, 37.0 degrees Celsius. So let me see what that gives. Oh, by the way, this should be 21.3, not 2. Keep slipping up. Okay, so this is going to be 21.3. Okay, so it is going to be 37.0 minus 21.3. And according to my calculation, this works out to be equal to 15.7. I'm just going to write it right here. 15.7 degrees Celsius. And that will be the answer. All right. And if you look at the numbers, it makes sense because the initial temperature is 37. The final temperature is lower, which means that the ring must have given off heat in that process, right? Okay. Any questions about this? Any questions? Any questions? Okay. Moving along. Now, here's an interesting example. It says here that you start off with 15.5 grams sample of a metal alloy, which has already been heated to 98.9 degrees Celsius. And then you drop it into 25 grams of water in a calorimeter. The temperature of the water rises from 22.5 to 25.7. Calculate the specific heat of the alloy. Okay, so let's see what's happening here. We have a metal, which is at 98.9 degrees Celsius, right? We drop it into water. The water is at a temperature initially of 22.5 degrees Celsius, right? So what's going to happen is that the hotter metal, when added to the water, will lose heat to the water, right? So basically what will happen is that the temperature of the metal will fall and the temperature of the water will rise until they're both the same. So we call that thermal equilibrium, all right? Basically what that means is that the heat that is transferred from the metal to the water will be the same in magnitude. So in other words, whatever the heat loss of the metal, the heat gained by the water is the same, right? In terms of magnitude. So we can represent that state of affairs by writing this down. The heat change for the metal will be equal to minus the heat change for the water, right? And the reason why we have the minus sign is because the metal is losing heat, right? So as far as the metal is concerned, its heat change is negative, excuse me. And as far as the water is concerned, its heat change is positive. Now, let me remind you that Q is equal to M times C times delta T. That's the equation we'll be working with. In fact, what we'll be doing is basically plugging this equation into this expression here. So we're going to have we're going to have this here for QM and the same thing here for QW. The only difference is that the values would be different in terms of the specific heat and the masses and the temperature change. So for QM, I'm going to write the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And that's on the left side. And then on the right side, I'm going to put minus the mass of the water times the specific heat of the water times the temperature change of the water, all right? Now, what the question is asking for is the specific heat of the metal alloy, which is a CM. So what I would do is to isolate it on both sides or on one side by dividing both sides by the mass of the metal times the change in temperature of the metal, like this. So that this, oh, this should be M here. So that this will cancel out with that. This will cancel out with that. So basically you're left with Cm, the specific heat of the metal, equals to all of this right here. So now we're going to calculate Cm directly. What we're going to do is put the numbers in. Now, let me just say that you have to be careful about doing this. You have to make sure that you place the numbers in the right position. So in the case of the water, the mass of the water is 25.0 grams, according to the information provided, times the specific heat of water, which you'd have to be provided with, which is 4.18 joules per gram degrees Celsius, multiplied by the change in temperature of the metal. Now, what's the change in temperature of the metal? It will be the final temperature minus the initial. The initial temperature is 98.9. The final temperature is 22.5. All right? So basically, you're going to put here 22.5 degrees Celsius minus 98.9 degrees Celsius. All right? So this underscores the importance of understanding where to put the correct numbers. All right? Then below, we have the mass of the metal. What's the mass of the metal? 15.5 grams. And then we have the change in temperature of the metal, which would be the 25.7 degrees Celsius, degrees Celsius, minus the 22.5 degrees Celsius. Okay, and then we do the number crunching. Of course, some units will cancel out. In fact, the gram units will cancel out here and here. In fact, what I'm going to do first is work out what's within the parentheses. So for the numerator, we have in parentheses 22.5 minus 98.9. And according to my calculation, I got minus 76.4 degrees Celsius. And then down here, it will be 25.7 minus 22.5. And according to my calculation, this works out to be 3.2. And then I do the rest. So 25 times 4.18 times 76.4 minus, and then I divide that by 15.5, divide that by 3.2, and then I'll remove the minus sign. And according to my calculation, something is wrong here. Hold on, wait a minute. Something is wrong here, and I'm not sure. Okay, I made a mistake. Because this is for the water. The final temperature for the metal will be 25.7, not 22.5. My mistake. So let me erase this here. I apologize for that. So this should be 25.7. So that means that 25.7 degrees Celsius, let me do this now, 25.7 degrees Celsius minus 98.9 gives 73.2. So let me erase this here. So this would be minus 73.2 degrees Celsius. Okay, so let me go through this again. Oh, shoot, hold on. I'm making a whole lot of errors. I apologize. I apologize. This should go here and this should go here. Okay, so let me explain what I am doing now. Okay, so basically, the change in temperature of the water is what I should have here. That should be 25.7 degrees Celsius minus 22.5 degrees Celsius, all right? And then down here would be the change in temperature of the metal, which would be the 25.7 degrees Celsius minus the 98.9 degrees Celsius. I don't know what I was thinking. Okay, so now everything is correct in terms of the setup. 25.7 minus 22.5. According to my calculation, this would be 3.2 as I calculated earlier. And then 25.7 minus 98.9. So this part gives the minus 73.2 degrees Celsius. And then I do the rest of the calculation. 25 times 4.18 times 3.2, and then divide by 15.5, divide by 73.2 minus, and then I put a minus sign in front of that. And according to my calculations, the answer becomes minus, I'm sorry, not minus, 0.29. And in terms of the units, the degrees Celsius will cancel out here and here, which means that the final units would be joules per gram degrees Celsius, and that's it. All right? So that's how that is done. So as you can see, especially since I made so many errors, it's very important that you understand where to put what numbers, all right, in order to get the right answer. All right, any questions about this? Any questions? Okay, moving along. So now we're going to talk about measuring enthalpy changes for chemical reactions. And this is where calorimetry becomes very important experimentally. All right, so if you have a reaction that is carried out in a calorimeter, key thing you need to remember is that whatever the amount of heat that is produced by the reaction, that's the amount of heat that is absorbed by the calorimeter, all right? And the opposite is true. If the reaction absorbs heat, then that means that the calorimeter is producing heat that is absorbed by the reaction. So basically we can write down this as the relationship between the heat change of the reaction and the heat change of the calorimeter, right? Q of the reaction is equal to minus Q of the calorimeter, all right? And of course, Q of the calorimeter can be expressed as the equation we are now familiar with, M times C times delta T. So basically, we can use this idea to basically measure the heat of the reaction, right? All we have to do is carry out the reaction in the calorimeter. We need the mass of the total mixture, the specific heat, and we need to measure the change in temperature as the reaction is taking place. And then we put the numbers into this equation that gives us the heat change for the calorimeter, and therefore Q of the reaction, the heat change of the reaction, would be the negative of that value, all right? So that's basically what we use to experimentally determine the heat change of a reaction. So here is one example, and I'm going to need some space for this one. So how am I going to do this? Let me get out of this here. Oops. Okay, let me do this. On. All right, so the question says, a 50 ml sample of a 0.250 m hydrochloric acid solution at 19.5 degrees Celsius is added to a 50 ml of a 0.250 m solution of sodium hydroxide. Now, and it's at the same temperature, all right? And then when the two solutions are mixed, the temperature rises to 21.21 degrees Celsius, and you're to calculate the heat of this reaction. Okay, so the way I would do this is, now this question is kind of, the information provided kind of make things a bit easier because they gave you the volume of hydrochloric acid and sodium hydroxide, which have the same molarity. So basically you can calculate the moles using those two numbers, the 50 and the 0.250, and you'll be doing that calculation for both hydrochloric and sodium hydroxide. So let's do that. I'm just going to say that the number of moles of HCl will be equal to the number of moles of sodium hydroxide, which will be equal to 50.0 mils, which we have to convert to liters, 1 liter over 1,000 mils. And then we multiply by the molarity, which is 0.250 moles for every 1 liter, right? So let's see what that gives. So that's 50 divided by 1,000 times 0.25. So according to my calculation, this works out to be equal to 0.0125 moles, all right? And that would be the moles of sodium hydroxide, which is equal to the moles of hydrochloric acid, okay? Let me see what next. Okay. Okay, the only thing that's missing here is, oh, okay. Now I know what to do. Okay. So basically, we're going to use the equation Q is equal to M times C times delta T, right? Let me write that up here. Q is equal to M times C times delta T. Okay. Now, we have to make some approximations here. So I'll explain what I mean. If you recall, the question says that you're mixing 50 mils of each solution in one. So therefore, the total volume of the solution is going to be 50.0 mils plus 50.0 mils, all right? So that's going to be equal to 100.0 mils. So based on that, we can calculate the mass of the solution resulting. So mass of solution will be equal to the volume, 50.0 mils, multiplied by the density. Now, even though it is not pure water, because it's a solution of both hydrochloric acid and sodium hydroxide, we can assume that the density is going to be the same as water, because it is usually the case for such solutions, right? So I'm going to put 1.00 grams here, multiplied by 1 mils, and that will give you 50.0 grams, right? So that would be the mass that you're going to use to plug into that equation. So Q of the reaction would be equal to 50.0 grams. And again, we're going to assume that the solution is dilute, and therefore the specific heat would be the same as that of water. And then we're going to multiply by the temperature change. Now, what is the temperature change? According to the question, the temperature was 19.50 degrees Celsius before, and it increases to 21.21 degrees. So that's 21.21 degrees Celsius minus 19.50 degrees Celsius. Excuse me. Now, I just realized that I misspoke a bit. The Q here is not Q of the reaction, it's Q of the calorimeter. So let me erase this here. So this will be Q of the calorimeter, right? So let's see what this gives. So that would be 50 times 4.18. Oh, you know what? Let me work out what's within the parentheses first. 21.21 minus 19.50. So according to my calculations, this part works out to be 1.71 degrees Celsius. And then I'm going to multiply that by 4.18 times 50. So rounded off to 3 sig figs. According to my calculation, that would be equal to 357 joules. All right? So that is the amount of heat that is absorbed by the calorimeter. That would be equal to minus Q of the reaction, right? So therefore, Q of the reaction, which is what the question is asking for, would be equal to minus 357 joules. All right? So that answers that question. Let me just do a quick check here. Yes. So that answers the first question on this page. Now, the second question, well, firstly, any questions about what I just did? Any questions? Okay. So the second question says, express the result of the previous question for molar amounts of the reactants and products. That is, determine the value of delta H that should be written in this equation right here. So this is the reaction between the hydrochloric acid and the sodium hydroxide. And what the question is asking for is the delta H here. Key thing you need to note and remember about this is that whatever the delta H that you're going to calculate here must represent, oh shoot, my battery is running down. I forgot to plug it in. Let me do this quickly. Okay, so as I was saying, what the question is asking for the delta H, is the value for this equation as it is written, where it says 1 mole of HCl reacts with 1 mole of sodium hydroxide to produce 1 mole of sodium chloride and 1 mole of water. So what does that mean? That means the value that we calculated in this result right here, this value is for 0.0125 moles of both sodium hydroxide and hydrochloric acid. So for 1 mole, let me write that down, for 1 mole of NaOH and HCl reacting, delta H would be equal to this value here, which is minus 357 joules, divided by the mole value that we calculated right here. So 0.0125 moles. All right. So let's see what that gives. That would be 357 negative divided by 0.0125. And according to my calculations, this works out to be equal to minus 2.86 times 10 to the 4 joules. And that's basically how that is determined. So basically, the value that should go here would be minus 2, wait, what did I say? Minus 2.86 times 10 to the 4. So the value that should go here is minus 2.86 times 10 to the 4 joules. So that's how that is done. Okay, any questions about this one? Any questions? Okay, what time is it? 10:05, okay. All right, continuing. By the way, did I give you guys the handout for this chapter? Okay, all right. Because I'm thinking, let me see here. Let me see if I can bring that assignment up. That's assignment number 6. So based on what we have covered so far, you should be able to do all questions up to and including question number 8, right? So, you can try all those questions up to number 8. And if you have any problems while attempting those questions, feel free to contact me if you need help. All right, so let me continue our discussion here. Now, we talked about calorimetry, which is basically the method that is used to measure heat flow. And we have different levels of sophistication in terms of a calorimeter. I think the one that I showed you earlier is, I think I described it as the ultimate in low tech. Basically 2 styrofoam cups, and that's it. You have a cover, you have 2 holes, one for the thermometer, one for the stir, and that's it. We use that typically when we're doing measurements of heat generated in a neutralization reaction like the sodium hydroxide hydrochloric acid reaction. Now, some other reactions require more a greater level of sophistication, such as this one right here. Now, this is called a bomb calorimeter, and this is used to measure the amount of heat that is generated in the combustion of an organic compound, right? So some more things have to be added to the apparatus. So we have what is called a steel bomb. This is where the reaction takes place. In fact, your sample would be right here on this this plate, and you're going to have 2 wires leading to it, connected to an external circuit. The purpose of that is to ignite the substance that you're analyzing. So when you ignite it, of course, you know, for all organic compounds, you're going to get heat generated, carbon dioxide and water as well, and maybe some other compounds depending on the composition of the organic compound. In any case, the heat generated here will pass through the walls of the steel bomb and enter into the surrounding water right here, where you have your thermometer and you have your stirrer here. Of course, the role of the stirrer is to make sure that the heat is evenly distributed in the water, so the correct value can be recorded in on the temperature right here. And that's basically the setup for the bomb calorimeter. So as you can see, it's a bit of a modification from the simple calorimeter, which I introduced to you guys earlier, right? Important for you to notice is that this reaction is carried out at constant volume. So what does that mean? That means Q minus Q of the reaction will be equal to Q of the calorimeter, which will be equal to just the change in internal energy, right? Now remember, internal energy, I'm sorry, Q would be equal to internal energy change plus P delta V. But because V is zero, or I should say delta V zero, this is zero, right? So that's why in this particular situation, Q is only equal to delta U. However, and remember also that Q in this particular, well, Q is basically equal to H, where delta U plus P delta V would be equal to H. But this would be a good approximation of delta H for the reaction, again, because this is done in a constant volume environment, all right? Okay, so that's basically what happens in a bomb calorimeter. Okay, so this is where things get interesting. Let's talk about this particular law. It's called Hess's law, and this law is actually based on the first law of thermodynamics. The first law of thermodynamics says that in any chemical or physical process, energy will be created from one form to another, so you'll never have the creation or destruction of energy in any physical or chemical process. Now, this is important. Hess's law is important because even though you can write down an equation for a reaction, sometimes in practice, it's very difficult to actually perform that reaction to measure any heat change, right? Sometimes it's a matter of the nature of the substances or whatever, right? However, we can determine the enthalpy of such a reaction without carrying out that experiment by relying on data carried out, well, from experiment carried out from other related reactions. So we're going to give a simple example, and we can move on to more complex. So let's say we want to carry out this reaction here, right? The reaction between carbon and oxygen to form carbon monoxide, right? Problem with this reaction is that it's very difficult to stop at the carbon monoxide, right? Because what's going to happen next is, what's going to happen next is that the carbon monoxide, let me just do a little quick thing here. The carbon monoxide will react with more oxygen to form carbon dioxide, right? So it's very difficult in practice to basically stop at the carbon monoxide stage for the purposes of determining the enthalpy change of this reaction, all right? So because enthalpy change is a state function, the enthalpy change of a reaction is the same whether or not the reaction is carried out in one step or through a number of steps. And this is basically what Hess's law is all about. As stated here, Hess's law says if an equation can be expressed as the sum of two or more other equations, the enthalpy change of the desired equation is the sum of the enthalpy changes of the other equations, right? So that's basically what Hess's law is saying. Basically what Hess's law is saying is that if you have, let's say, let me get out of this here, just to give a simple example. And let me go back to this here, and let me get rid of this here. Okay, so let's say you have a reaction A going to B, right? And let's say you have another reaction B going to A, right? I'm sorry, B going to C, all right? So let's say that this is delta H1, the enthalpy change for that is delta H1, and the enthalpy change for that is delta H2, right? what Hess's law is saying is that if you add these two equations together, obviously the B's will cancel out to get the net reaction, which is A to C. Then the delta H value for this, I'm going to call this delta H3, would be equal to delta H1 plus delta H2. That's what Hess's law is basically saying, right? Another way, some people have different ways of visualizing this. Another way of representing this, you can have, how should I write this now? A going to B, and then B going to C, right? Or you can look at A going directly to C, right? So this would be delta H3, this would be delta H1, and the enthalpy change here will be delta H2. Again, going from A to B to C is the same as going directly from A to C. So therefore, delta H3 will be equal to the sum of these two, which is what we have here. All right, so that's basically what Hess's law is saying. All right, so that's a hypothetical example. Let's look at a real example. And the real example is related to what we were just talking about with respect to the reaction between carbon and oxygen to form carbon monoxide. So here's a diagram which shows you what's happening here. So this is what we are trying to find, right? But it's very difficult to carry out the reaction where carbon reacts with half a mole of oxygen to form carbon monoxide, right? Very difficult because you can't stop the carbon monoxide from reacting with the other half mole to form carbon dioxide, right? So how do we determine this? Well, going directly from carbon to carbon and oxygen to form carbon dioxide, this is the amount of enthalpy change occurring. Going from carbon monoxide to carbon dioxide, this is the enthalpy change, right? And basically, based on these three delta H values, we can say that delta HC, applying Hess's law, is equal to delta HA plus delta HB, right? And since we want to find delta HA, we can rearrange this to get delta HA is equal to delta HC minus delta HB, right? So as it says here, we can find delta HA by subtracting delta HB from delta HC. So all we have to do is put the numbers in, minus 393.5 kilojoules minus 283.0 kilojoules, and whatever that gives, that will be the answer, right? So basically, without carrying out this reaction right here, without carrying out this step, but knowing the values for this step and this step, we can calculate the enthalpy change of that step. So that's one of the useful attributes of Hess's law. You can, based on other equations, calculate the enthalpy change of a particular reaction, which you don't need to carry out in order to determine that. Okay, now that's a simple example. I want us to look at this example, which is a bit more complex. And for this one, I'm going to need some space. What I'm going to do is copy all of this here. And by the way, this question I'm about to do is a typical Hess's law question, right? So if you understand this, any question I give you in a future exam, you should be able to do it. Let me choose Word as, okay. So oh, wait a minute. Look like I copied something from earlier. Go back to the PowerPoint. Control C. Then I go to Word. Control V. Okay, so this is a question right here. All right, so here's a question. And it did not completely replicate what was there before because these should be delta. All right, so please keep that in mind. All right. Okay, so this is a question. It says, calculate the enthalpy change for the reaction A, which is this reaction right here, right? Delta H is what they're asking for. Given the data in equations B, C, and D. So they gave you these equations here, and they gave you their corresponding delta H values. Okay, so this is the way you'd approach solving this kind of problem. What you're going to do is look at each of these and make sure that this is in the right color. Okay, so what you're going to do is look at each of these equations, right? And compare it to the equation for which you're trying to find delta H, right? And then you're going to make the following changes, starting with B, right? So basically, if you compare B to the first equation, right? You see that they both have carbon on the same side, okay? But the difference is, in the case of the first equation, there's a coefficient of 2. So what I would do to this equation is that I would multiply right through by 2. So I'm going to get 2 carbon solid plus 2 O2 gas to give 2 CO2 gas. And because we have doubled everything here, we have to also multiply the delta H value by 2. So delta H for this new equation would be 2 times minus 393.5 kilojoules, right? So that's basically what we do. Because, and the reason why we did that is because we have 2 carbons here in the first equation. So we multiply this carbon by 2, but you have to multiply also the entire equation by 2, right? And this would be the result. Okay, next thing we do is compare this equation to the first equation. And what do we notice they have in common? They both have C2H4. We have C2H4 here, and we have C2H4 here. The difference is the C2H4 is on the left side of the equation, while in the original equation, the C2H4 is on the right side. So what do we need to do? We need to flip this equation to get the C2H4 on the right side. So when we flip it, you're going to end up with 2 CO2 gas plus 2 H2O liquid. And then on the right side, we're going to have C2H4 gas plus 3 O2 gas. And what does that mean for the delta H value? The delta H value would have to have its sign change from negative to positive. So delta H would be equal to, in this case, 1410.9 kilojoules. All right? Okay, and then now we get to the third and final equation that we need to mess with. And what do we see when we compare this equation, D, to equation A? We notice that they have in common H2. However, we have 2 here as the coefficient in front of the H2 in the original equation, which means that we need to multiply this equation by 2. So when we do that, you're going to end up with 2H2 gas plus O2 gas to give 2H2O liquid. And the delta H for that would be equal to 2 times minus 285.0 kilojoules. All right? I'm sorry? Where? You mean this? No, that is, I think that is actually, you said what, 20? It should be 285.8. Oh, 8. My bad. You're right. Okay. So, now that we have done all those changes, what we need to do is add all these equations up, right? Now, after adding all these equations up, the net result should be this, right? So the delta H value that you're going to get would be the result of adding this to this to this. But let's make sure that these all add up to give you that final equation. Now, remember, when you add up equations, you cancel out items that are common to both sides, right? So in this case here, these 2 carbon dioxide molecules will cancel out each other. These 2 water molecules will cancel out each other. And let's pay attention to what's happening with the oxygens. You have 2 plus 1, 3 oxygens on the left side, which will cancel out with the 3 oxygens on the right side. And there's nothing else left to cancel out, so we're left with 2 carbon solid plus 2 H2 gas on the left side. And on the right side, the only thing that remains would be C2H4 gas, right? And that is exactly the same equation as the original equation, which means that now we can calculate the delta H value by adding up all these values that we determined earlier. So 2 times 393.5 5 minus, and then we're going to add that to 1410.9, and then we're going to add that to 285.8 minus, oh shoot, okay. You know what, let me do this piecemeal. So 2 times 393.5, okay, so this gives minus 787.0 kilojoules. And then this part here would give you 285.8 minus times 2. This gives minus 571.0 kilojoules. And then we add all of these up. So minus 571.0 plus 1410 minus 787.0. So according to my calculations, this works out to be equal to delta H here, works out to be equal to 52.0 kilojoules. And that's how I do that. So that's basically the approach, the typical approach that you take for a typical problem of this type. And I think in the assignment I've posted that I provide for you guys, let me see how many questions of that type are there. Okay, so number 9 is one such type. Number 10 is another such type of question. And number 11. So now you should be able to do all questions up to number 11, all right? Okay, so moving along. Okay. Okay, so let me go back to full screen. Okay, so we have done that question. So now we're going to talk about what we call standard enthalpies of formation. Now, the thing about enthalpy is that you cannot measure the enthalpy of a particular compound or substance, right, directly. And the main reason why is because in order for you to measure any heat change or any enthalpy value, it's always in relation to another substance, right? It's always a relative thing. So basically what was decided was to, by the powers that be, was to define what we mean by standard enthalpies of formation, just to basically have a meaningful way of comparing, you know, heat changes and reactions. So as stated here, it would be, if it's possible, convenient to measure enthalpy change by simply finding the difference between the H of the reactants and H of the products. But as I said before, that's impossible because enthalpy, we cannot know what the absolute values of enthalpies are. So what was decided is that a steady state of a substance is defined where basically this the state is under the conditions of 1 atmosphere and temperature, which is 25 degrees Celsius, right? So that's a steady state. And this should not be confused with STP, which we talked about in the previous chapter. STP is for gases. Steady state is pretty much for every substance. And one big difference between STP and steady state is that STP says that the standard temperature is 0 degrees Celsius. Here, it's 25 degrees Celsius. So please keep that in mind, right? So basically, all the enthalpy changes that we're talking about here, when we talk about standard enthalpies, are measured under those conditions. So that's the definition right here. The standard enthalpy change for a reaction is the enthalpy change in which reactants and products are in their standard states. In other words, the state where their conditions are described earlier as standard conditions, right? And then there's another term that I need to talk about called the standard enthalpy of formation for a substance, which is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states. And you'll notice in both symbolism, there's a small o here, or 0, which is written as a superscript, right? That means standard condition. So whenever you see that, you immediately understand that the conditions are 1 atmosphere if there are any gases involved, and the temperature would be 25 degrees Celsius. Okay, so when we're talking about the standard enthalpy of as we said before, excuse me, is the standard enthalpy for the formation of 1 mole of a compound. So for example, and I should say for 1 mole of the compound from its elements, from its constituent element, right? So for example, let's say we want to determine the enthalpy of formation of methanol. Then the equation that we're talking about is the equation where we start off only with the elements and they come together proportionally to form that one compound. So in the case of methanol, you're going to need 1 mole of graphite or carbon, 2 moles of hydrogen, and half a mole of oxygen to give 1 mole of methanol, right? The enthalpy change for this equation is minus 238.7 under the standard conditions. So therefore, we can write down that delta H standard for methanol, for the formation of methanol, is minus 238.7 kilojoules, all right? So that's basically how we determine that value. Based on that, if we were to do that for pretty much all substances, we can treat those enthalpy of formation values as if they're absolute values, and we can use that to determine enthalpy changes for a wide variety of reactions. And I think the next slide has some examples. Now, before we get to that example, I want to point this out, and then I want to show you the table where we can get these values. What is the question being asked? What is the enthalpy of formation of an element in its standard state, right? For example, oxygen or nitrogen or boron, right? What would be the enthalpy of formation given the definition that we talked about here? Remember, the definition is that the standard enthalpy of formation is the enthalpy of formation of 1 mole of a substance from its elements when both reactants and products are in their standard states, right? So in the case of oxygen, for example, what they're saying is if you have oxygen here as a product and you start off with oxygen as a reactant, what's the enthalpy of formation under standard condition? And the answer is 0, no change, right? If there's no change, then there's no enthalpy of formation for an element under standard condition, right? And that is true for exactly every single element, right? The enthalpy of formation under standard condition is 0, right? And that's important for you to note. So let me just show you this table right here. It's, again, posted in Canvas. So let me go here. Go to Files. Well, let me close this first. Then go to Tables. And of course, you'll have access to this table in your future tests. So this is the link right here, thermodynamic data, right? So if you open that up, you're going to see a table which gives you a list of elements and compounds. Let me just check something here. I think it's listed in alphabetical order. Yes, it is listed in alphabetical order, right? So let me go back to the top here, right? Now, for all purposes in this course, we will not be concerned with the last 2 columns here. We'll be only concerned with the enthalpy of formation part of it, right? And for different substances, there are different values for the enthalpy of formation. Now, remember what I said before. For elements, the enthalpy of formation standard is 0, right? And you can see that in this table. You have aluminum, 0. Arsenic, 0. Barium, 0. For every element that you see here, boron, bromine, calcium, and as you go down the line, every single element has a standard enthalpy of formation value of 0, right? That is not true for the other substances, as you can see, all right? So this is a table that you'll have access to in order to use these values to determine the enthalpy of a reaction, all right? So I'm going to go back to the PowerPoint, and I think the next slide is And well, before we get to the example, this is just basically describing how you would use the standard enthalpies of formation to carry out these the calculation of the enthalpy of reaction. So basically, it's based on this equation right here. The enthalpy of the reaction will be equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants, right? Now, you'll notice that there's this Greek letter nu here and nu here. Those values represent the coefficients of the different substances in the balanced equation, right? So what this is suggesting is that as you add the enthalpy of formation of the products, in each case, you have to multiply those values by their respective coefficients, right? And the same would be true for the reactants as well. You're going to see that in the example that we're about to do, right? So basically, once you find that sum of the enthalpy of the products, find the sum of the enthalpy of the reactants, you subtract the sum of the enthalpy of the reactants from that of the products, and that will give you the enthalpy change of the reaction. And this is a more easier way compared to using Hess's law, which can work, but is much difficult, all right? So the next slide is an example. Let me copy this here because, again, I'm going to need space for this. Control C, okay. And then let me go here. No, not there. I'm going to use Word again. And I'm going to lasso as much of this as I can. Lasso all this here. And then, okay, so this is the question. And it says, it gives you this equation. And it says you need to determine delta H for this reaction using the standard enthalpies of formation in the table that I just showed you, all right? So what I'm going to do first is write down an equation, which basically is how you're going to find delta H of the reaction, right? Under standard conditions. So remember now, enthalpy change would be the total sum of the enthalpy of the products minus that of the reactants. So we're going to start with the products first, the first of which is carbon monoxide. So I'm going to write down here 4 times the enthalpy of formation of carbon monoxide gas. And then to that, I'm going to add 8 times the enthalpy of formation of H2 gas. So those are your products. I'm going to put them in square parentheses. And then from that, I'm going to subtract the sum of the enthalpy of the formation of the other substances, the reactants, starting with methane, 3 times the enthalpy of formation of methane, CH4, plus 2 times the enthalpy of formation of H2O liquid. And I don't know if I mentioned this to you guys the last time, but whenever you're doing these problems, pay attention to the states, right? Because the enthalpy of formation of a liquid would be different from that of a gas or a solid for the same substance. So pay attention to that. And then the next substance is carbon dioxide. There's only 1 mole of it represented, so enthalpy of formation of CO2 is all I'm going to put here, gas. All right? And then I'm going to put that in square parentheses as well. Okay, so now it's all a matter of putting in the numbers here. So that means we have to go to the table. I'm going to see if I can do a little side-by-side thingy here. Okay, so get rid of this thing here first. Okay, so let me put this aside here. Let me squeeze this in here. Oh, no, that won't work. Okay. Okay, I guess this is the best I can do. Okay, so the first thing I'm going to do is look up the value of the enthalpy of formation of carbon monoxide. So, as I said before, I think this is in alphabetical order, so that should be, okay. So here's a value for carbon monoxide. It's going to be 4 times minus 110 point, what was it? 110 point, I lost it, carbon, 0.53, okay, so 0.53 kilojoules, all right? And then to that, I'm going to add, oh, we can make life a bit easier. You know why? Because hydrogen is an element. So therefore, that's 0. So I'm just going to put 0 here. And then that takes care of the products. And then on the reactant side, we have 3 times the enthalpy of formation of methane. Oh, and another thing I need to mention here. This table here has a special last page, which basically deals with organic compounds. And methane is organics. Let me scroll down. So I'm talking about here, right? Methane, the enthalpy of formation is minus 74.81. So let me put that here. Minus 74.81 kilojoules. And then that takes care of, oh no, actually, hold on. I jumped the gun. Where's the eraser? Urgh. Let me take out that square parentheses. Okay, going back to the table. Now I need to look up the value for the enthalpy of formation of H2O liquid. So going back to the table here, let me see here, H2O liquid, minus 285.83. So 2 times minus 285 plus 2 times minus 285.83, this should be minus, kilojoules. All right. And then the last substance is carbon dioxide. So let's scroll up. Carbon dioxide gas, minus 393.51. So plus minus 393.51 kilojoules. And that's a setup. All right. All we have to do is do the number crunching. But I would recommend that you work out what's the separate parts first. So what I'm going to do is multiply 110.53 minus times 4. So this will give you minus 442.12 kilojoules. That is 0, so we don't need to worry about that. And then I'm going to put 3 times minus 74.81. And that gives minus 224.43 kilojoules. And then to that, I'm going to add 2 times minus 285.83. And according to my calculation, that gives minus 571.66 kilojoules. And then finally, oh, we don't need to multiply by anything. That would be minus 393.51 kilojoules for the carbon monoxide. So this is basically, well, what it comes down to. So let's add up all of these. So 442.12 negative minus, oh, by the way, this should be, all of this here should be within square parentheses. So what I'm going to do is work out this part first. So minus 224.43 minus 571.66 minus 393.51. So according to my calculation, all of this here works out to minus 118 9.6 kilojoules, well, 60 kilojoules, and I still have minus 4 for 2.12 kilojoules minus this. So that means it's plus, well, let me put plus there, and then minus 442.12. And according to my calculation, this works out to be equal to 747.48 kilojoules. And that's how that is done. So that's basically how you can determine the enthalpy change of a reaction based on the table, right? The table gives you the standard enthalpy of formation values, right? And it's very simple, even though it's kind of tedious because, you know, you have to multiply each of them by their respective coefficients. But it comes down to basically the total sum of the enthalpies of the products minus the values for the reactant. That's basically what it comes down to, all right? Okay, any questions about this? Any questions? All right. So this would have to be the last thing that's left. We're pretty much completed the chapter. There's one more question, which you can try on your own because it's simply based on what we just did. The only difference is that they gave you the delta H value, right? Which is what you're trying to find here. And they're asking for you to determine the enthalpy of formation of this molecule right here, which is known as isopropyl alcohol, right? So basically, again, it's products minus reactants, but this time one of the reactants is not known in terms of the enthalpy of formation, but you do know the enthalpy of the reaction. So you should be able to rationalize how to determine that. So you can try that on your own. If you have any questions, let me know. So at this juncture, oh, and by the way, one more thing. Did I give you, when I gave you that assignment, did I give you the, because I just saw it this morning. Hold on. Did I give you this? There's an additional, okay, well, you can go online. Basically, when you're through doing these, attach this to this. It's basically because when I put this together, I forgot to give an example of the type of problem I just showed you. So I created another document, which is basically the same chapter. So just attach both of them together and turn them in. If you have any questions doing any one of these, let me know, and I'm more than willing to help you, all right? So that's it for today. And nobody else came, huh? Let me see here. Nobody else came. Anyway, okay. All right, that's it for today. I'll see you on Thursday.